Example 4. A Ferris wheel has radius 15 meters and rotates once every 120 seconds, and the passengers get on at the bottom, which is 1 meter from the ground. Part A asks, determine the cosine equation for the height of the passenger of the Ferris wheel as a function of time. So what I've done over here is I've drawn the picture of the Ferris wheel, and we know that it's 1 meter from the bottom. So I've shown the cosine graph at 1 meter high to start with, and we can see that the bottom of the Ferris wheel represents the 1 meter height. It has a radius of 15, so it's going to go to the middle. I have the 16 meters. That's where the axle of the Ferris wheel will be, and that's where the middle of the graph will be. And it goes up and down the radius of 15. So that's going to be my amplitude. So my amplitude is 15 meters, and I can see that that would be the radius of my Ferris wheel. So I need to come up with the cosine equation for this. So I need to know the amplitude. I need to know the vertical shift. So I have that already. So what I'm going to do is I'm going to start writing the function here. So the height as a function of time is equal to, I'm going to use a cosine function. It's going to be upside down. So it's going to, with a radius of, or a value or amplitude of 15. So I'm going to start with my amplitude of 15. Because it's upside down, I need to put a negative in front there. And this is going to be the cosine. I have to have a horizontal shift and my compression factor in there. But my vertical shift, or the middle of the graph, is going to be at 16. So there's my two parts. There's the middle and my radius showing up. Okay? So now I have to figure out the horizontal shift. Well, in this case, the horizontal shift is going to be 0 because I'm starting at the bottom, which is at 0 time. I'm at the very bottom. My period is going to be 120 seconds. So this represents one period, and the t is 120 seconds. Well, if that's the case, then I can write this in my cosine equation. I can just write this using the b of 2 over 120, where the 120 represents the period. And so that's going to be times by t. So that blue represents my horizontal compression factor. And this then is the equation of the Ferris wheel, the height of the Ferris wheel as a function of time. Part B says, what is the height at 45 seconds? Well, if I take a look at the full circle, well, it takes me 120 seconds to get around the full circle. So I've marked the 90-degree parts with the seconds. And if I were to draw in 45 seconds here, 45 seconds is going to be right at that angle right there. So there's my 45-second point. And that angle then, if I look at that angle in that standard position, that's going to be my 3 pi over 4 angle, and that's going to give me negative 1, 1, and root 2 here. So if I want to find the height of this at 45 seconds, I just need to calculate the value of this at 45 seconds. So I'm just going to plug it into my equation. So I'm going to end up with negative 15 cosine, and that angle works out to be 3 pi over 4. So if I plug in 45 seconds into here, I get 2 pi over 120 times 45 plus 16. That's going to work out to that the angle is going to work out to be 3 pi over 4. So this is cosine, and this inside piece here, when I work this out, I get 90 over 120, which is 3 pi over 4. Okay, plus 16, and working this out, I get negative 15 times negative 1 over root 2 plus 16, and that works out to be 26.61 meters. So at 45 seconds, if I were to draw 45 seconds in here, it's going to be, this would be 60 seconds here, 30 seconds here, so 45 seconds. That position right there represents a height of approximately 26.61 meters. Okay, so part C then says determine the times at which the passenger is 23 meters from the ground. So looking at this graph here, and I'm going to do this maybe purple, 23 meters from the ground is somewhere right about here. So there are 2 points on the Ferris wheel where we're going to be 23 meters from the ground. And that's going to correspond to these 2 points on my curve, and which relate to these times on the x-axis. Okay, it looks like somewhere between 30 and 45, and symmetrically on the other side of 60. When we set this up, we can set this up by solving this, because I know that I'm looking for the time where the height is equal to 23 meters. And that's going to be equal to negative 15 cosine of 2 pi over 120x, or sorry, t, plus 16. And I can solve this equation for the time. So solving this equation, I'm just going to clean this up a bit, plus 16. So solving this equation, I'm first going to subtract 16 from both sides, so I get 8. I'm going to divide by negative 15, so I'm going to get negative 8 over 15 is equal to the cosine. So cosine of 2 pi 120t. I need to solve for the angle, so I'm going to use the arc cosine. And that's going to give me the angle 2 pi over 120t, and that's going to be theta 1. Okay, so I'm going to do theta 1 in a different color here. So theta 1 from my calculator. So I'm going to write this as 2 pi over 120t as theta 1. This is from the calculator. I'm going to get 2.133 radians. Okay, and then solving for the actual time, if I solve this algebraically for the time, I get 40.74 seconds. Okay, so if I take a look at my graph here, that's this point here, 40.74 seconds. I also have to solve for theta 2. So I get 2 pi over 120t, and this is going to be theta 2. And that's going to be it's going to be 2 pi minus theta 1, or 2.133, and that gives me a value of about 4.15 radians. Solving this equation for t, so I times by 120, divide by 2 pi, and I'm going to end up with 79.26 seconds. And if I take a look at my graph over here, this position here represents 79.26 seconds. Okay, and that's symmetrical about the 60 seconds, because I can see that's the middle of the graph.